Okay, let's look at another example. Find the volume of a solid generated by revolving the region bounded by the graphs of the equations about the indicated axis. So you give you your function y equals cosine of x equals negative pi halves, x equals pi halves, y equals 0, and they want you to revolve it about the x-axis. So if you want to try to get a rough sketch of that, you can pause it and do so. Right here, I just kind of tried to sketch that out um, from negative pi over 2 to pi over 2, revolving about the x-axis. This would be if I selected a particular, this is about the x-axis, this is our representative rectangle is going to be perpendicular to our axis of revolution, so that's a dx. Now if I was to revolve this red disc about the region, you can see that it would make this type of a figure, and if I did mini disc all the way through there, we would get something that looks like that. Okay, so what we want to do is plug in our volume right there, so if you will set it up and then we'll check our answer. Okay, so hopefully you've gotten this far. We've just pulled the pi out front. We have from negative pi over 2 to pi over 2 our function squared dx. Okay, now we have an option. We can either calculate this as is, or we can see this picture. What else can we also use? Symmetry, right? We can use our symmetry because if I folded this thing in half, I can find the area of this side and multiply it by 2. So you have a little bit of an option there. So I want you to go ahead and work on evaluating this. Okay, so I'm going to use symmetry because the advantage in using symmetry is we get to have a 0, which makes our evaluations a little bit easier. But we have the antiderivative of the cosine of x squared. This would entitle some u substitution, or we can use a double angle formula for cosine squared theta, which is a trig property. And I'm just going to use this. I would give this as a hint, this double angle formula on a test, so we would replace that here. And then now we can go ahead and do some simplification here. So one thing I can do is I can say that, well, this 2 is going to cancel with this 2. And so I could say volume is equal to 1 plus cosine of 2 theta. 2x. Let's do 2x. 2x dx. Okay, now we want to take the antiderivative of this, the antiderivative of this, and keep going. Okay, correction real quick. Make sure you change that to pi over 2. I had a 2 there. So now we take the antiderivative of this is x. Cosine of 2x would be sine of 2x, and then remember we account for that inside part, that 2 right there. So you have a 1/2 sine of 2x. We evaluate it from pi 0 to pi halves. Okay, let's do the next part. Okay, so once we set this up, the blue is everything evaluated with the pi halves substituted in, and then the red is with the 0 substituted in. Let's start with this blue portion. These two cancels, so we get, what's the sine of pi? 0. 0 times 1/2 is just 0 plus pi halves. So the blue will simplify to pi halves. Okay, and then let's move to the right. 2 times 0 is 0. What's the sine at 0? Good. 0 plus 0, so we just get pi halves minus, let me put that in red, 0. So that's just going to be pi times pi halves over 2 would be pi squared over 2. Pi squared over 2, which is approximately 4.9348 units cubed. I just went back and added the scratch work of this so that it's on the PDF print out for how we got this term right here, the antiderivative, using u substitution if you need to refer to that. Okay, this next one you're going to have example 5, find the volume. This time we have x equals y squared, y equals 3, x equals 0, and we're going to go about the y-axis. So this time we're revolving about a different axis. So if you'll take a few minutes and sketch the graph of these, because this one's solved for x equals, it may be easier if you want to just do an xy table to plot some points. It's up to you. If I were to since my y-axis perpendicular to my axis of revolution would be a horizontal representative rectangle, which would be a dy region. I mean a dy variable. This would be, if I was to revolve this about the y-axis, we would get some type of 3D sketch like this one. Okay, so take a few minutes to sketch that out and then see if you can plug in the volume to set up the integral before we actually calculate this. Okay, so the first thing we have is just our variable we're working with, dy. We're revolving about the y-axis, so we see the changes here. Remember, our intervals are going to be in terms of the y. Our variables are going to be in terms of y. So in this case, we would solve equations for x equals, which this case it was already done, so that's nice. Our interval is going to be, remember to focus on the y. So from what, 0 to 3. Alright, so this is just going to be interval from 0 to 3. I'll pull the pi out front. Then this is going to be what? Y squared. Whoops, wrong way. Y squared. And then minus 0. So this is x equals 0. They give us a purple. The purple graph is going to be the next one. So we're going to go from the top one. And then we have our 0. Let me get over there. Okay, so check your work up to this point. You have your y squared squared. You pull your pi out, and then this just becomes y to the 4th dy. And when we evaluate the antiderivative here, you'll have from 3 to 0. So go ahead and plug those in and calculate. Okay, so you'll get 243 pi fifths, or approximately 152.68 units cubed. Okay, next we're going to be looking at the volume of a washer, but first of all, we briefly brought this up earlier because I had an example that was a little bit early for this, but basically if you have two functions, an f of x function that's given and a g of x function that's given, we can just have our outer radius minus the inner radius for our area part, then times the thickness. So we briefly mentioned this earlier in the lesson. The first example we're going to work at, and let me hide this screen, is going to be right here. Find the regions bounded by the graph of the given equation, revolved about the x-axis. So we're going to have a dx rectangle. Find the volume. So graph this, sketch a graph of this, and we're going to revolve about the x-axis. So pause this for a minute and make your sketches. Then when you finish, I want you to check your sketch here. So if I do a dx rectangle because it's perpendicular to my x-axis, I'm going to do the blue minus the purple right here, so the outer minus the inner. But to find my intervals, it needs to be in respect to the x-axis. So I need to find intersection points here and here. You can either do that algebraically or you can do that in your calculator. So I want you to take a few minutes and start with that part first. Okay, algebraically it wasn't bad this time, so I solved it and I get intersection points at x equals 3 and x equals 1. Negative 1, make sure you get that negative sign there. Okay, so that means have negative 1 and 3. We have our pi that we can pull out front. And let's look back and see what the topmost function is. What's the blue one? 2x plus 3, good, and then we'll do minus the bottom one, which is the purple one. Well, we tell top versus bottom by a representative rectangle, so let's set that up. So the top one, we're going to say 2x plus 3 squared, and then we're going to subtract, let's just do it in a different color, the bottom one, which was x squared squared dx. Whoa. Okay, next I want you to FOIL this out, and simplify this inside term. Okay, check your algebra there, and then this is going to be the antiderivative, so I want you to check your work here before you continue on, and the next is just going to be plugging in our values of 3 and subtracting out the values when we plug in -1 for x and solving. Okay, so you want to check your work on that, plug in all the values with when x is 3, and then subtract all the values when x is -1, and you want to check your calculations there.